Welcome to the second lecture in our series of lectures on Verilog RTL Modeling by example. In this lecture, we will be introducing the register transfer level or RTL abstraction, which forms the core of the HDL based digital design process. In this lecture, we will start with an introduction to the idea of abstraction in digital design. Next, we will take up the RTL abstraction in detail, which will be followed by an example of the serial multiplier design at the RTL abstraction. We will also briefly look at how an accumulator based CPU can be represented at the register transfer level. Finally, we will briefly look into the high-level synthesis, which is a process by which algorithmic descriptions are automatically translated into the RTL abstraction. Also, we will see how designs can be classified as Datapath Intensive or control intensive designs based on their characteristics. Abstraction or hiding is a very powerful tool that has been used by both the hardware and software community for a very long time for handling complex systems. We are all familiar with the gate abstraction, which is commonly used in designing gate level digital circuits. This was the basis for the traditional design flow using the TTL ICs. Now, in this level of abstraction, the lower level details and the complexities of transistor level circuit implementations are more or less hidden from the digital designer. Probably the only circuit parameter that the designer needs to know is the logic voltage and the drive currents and the various drive currents. So this abstraction has served the design community faithfully for probably around 2 or 3 decades. But with the advent of microprocessors and peripherals and ASICs and very complex systems which have now evolved to the level of SOCs, designers realized that the gate abstraction was not adequate for describing complex systems. On the other hand, we can describe a system at the algorithmic level of abstraction. So at this level, the description has the advantage that it specifies the complete functionality of the system. For example, you can use MATLAB for describing a digital signal processing system completely, especially with regard to its functionality. But the main drawback of these systems is that they don't provide any insight into the eventual hardware architecture which could be used for implementing such algorithms. In other words, they are said to be not cycle accurate. That is, we don't have any means by which we can estimate the number of clock cycles that it would take to execute a particular algorithm if it is implemented in hardware. So this particular information is not available from the algorithmic level of abstraction. Therefore, even though the complete functionality of the system is described at this level, it is of no use from the hardware architecture implementation perspective. So now we have two extremes. At the one end, we have the gate level of abstraction, which is an extremely lower level of abstraction where the architectural details of the system are not possible to represent. And also the functionality of the system is not evident from the gate level of abstraction. On the other hand, we have the algorithmic level of abstraction, which effectively describes the complete functionality of the system, but which doesn't provide any insight into the architecture that will be eventually used for implementing such a system in hardware. Now we come to what this lecture is all about, that is the register transfer level or RTL abstraction. So this is an intermediate level of abstraction between the algorithmic level and the gate level. We have seen that the gate level of description or abstraction is a very low level where the functionality of the system is not evident by analyzing the gate level implementation. On the other hand, an algorithmic specification like the MATLAB code or a C code will completely specify the functionality of the system but is not cycle accurate, in the sense that there is absolutely no notion of the hardware that could possibly implement such a functionality. So from the HDL point of view, both these levels of abstraction, that is the gate level and the algorithmic level, are not effective in describing a system which can eventually be modeled using an HDL. So now we have the register transfer level or the RTL abstraction, which has characteristics of both the gate level and the algorithmic level. It is somewhat similar to the algorithmic level in that it is able to capture the behavior of the system. At the same time, it provides a cycle accurate description of the system, so that in that sense it is more aligned towards the gate abstraction. So from this we can see that this is a level of abstraction which is somewhere intermediate between the algorithmic level and the gate level. Now this is considered to be an ideal level of abstraction for HDL, because it is able to capture the behavior of the system. And earlier we saw that HDLs are popular because they are effective tools for modeling the behavior of the system and modeling the behavior in such a way that eventually the model can be synthesized in hardware. So this is why the RTL abstraction is extremely important as far as HDL designers are concerned. Of course, later on we will see that we have current software tools which can directly parse an algorithmic description and generate an RTL level description of the same system. This is called high level synthesis. We will briefly look at high level synthesis at the end of this lecture, but later on we will have more sessions where high level synthesis is taken up in greater detail. The RTL abstraction conceives a system as being comprised of either data path elements or control path elements. The data path elements basically store and manipulate data in the system. For instance, if we look at a microprocessor, which is a typical digital system that we are all familiar with, the data path elements in the processor will comprise the registers in the processor, the ALUs in the processor, and the steering logic such as the multiplexers which route data to and from the ALU and the registers. The storage and manipulation of data in the data path is controlled by the control path elements. So we can say that the data path elements don't have any intelligence on their own. The control path elements generate control signals which eventually determine the way in which data flows in the data path. For instance, one example which we can think of is the addition of two numbers in a processor. We know that if an addition is to be executed in a processor, the data has to be stored in the processor registers. So this is an action which is carried out by means of certain control signals generated from the control path, which is typically consisting of the control bus and the state machine, which controls the execution of instructions. So we can say that the control path basically provides the intelligence in a system. So for implementing the control paths, we have components like state machines and special registers such as the instruction registers in processors. And for determining the decisions pertaining to the various control actions, we have status and flag bits. So the nature of the outcome of the data manipulation that is carried out by the data path will be eventually monitored by the control path. For instance, if there is an overflow during an addition process, this is not detected by the data path elements. The data path elements simply manipulate whatever data is stored in the registers. But the nature of the outcome in the form of either the generation of a carry or an overflow is eventually determined by the status and flag bits, which are read by the control path elements such as state machines. And these bits determine the subsequent action that is to be taken on an event like an overflow. So the nature of the action will of course depend on the seriousness of the event, like generating an interrupt or any other possible action. In addition to the state machines and registers and status and flag bits, we have the control buses, which form the medium of communication between the control path and the data path. So based on the assertion and deassertion of these control signals, the flow of data in the data path will be regulated. For instance, when an instruction is executed, when an instruction such as an add instruction is executed, the select lines for determining the source registers for the operands of the add instruction will be generated by the control path based on the opcode of the instruction. And also the select lines for determining the destination of the outcome of the add instruction will also be generated from the control path. To illustrate the RTL abstraction better, we use the analogy of a building pipeline system. So in a pipeline system, we can think of the water that flows through the system as the data. So the input data may be thought of as the water that flows into the pipeline system. Then the data that flows through the system is analogous to the water that flows through the building pipeline. The registers are represented by the tank which stores the water. And finally, the output data is represented by the analogy of the water flowing out of the pipeline in the form of drainage. So we can see that the water, as it enters the system and flows through the system and flows out of the system finally, assumes different forms. Likewise, in a digital system, the data that flows into the system is manipulated by the data path elements, of course under control from the control path, and it changes its form. The manipulation may be in the form of arithmetic operations like addition or subtraction or shifting. Eventually, the data is output from the system, either through the output buses or through the registers again. Now the various taps or valves which control the flow of water in the pipeline represent the control path elements. So we can use these valves to control the flow of water. In a similar fashion, the control path elements can determine the flow of data in the digital system. The operation of the control path elements in a pipeline is either by means of manual intervention. We can manually open and shut the valves that control the flow of water, or we can even have an automated system which provides the intelligence for controlling the flow of water. So these taps represent the control elements which control the flow of water, and they are analogous to the flow of data in a data path. Now we can also think of monitoring the quality of water that flows through the system. This is analogous to the status bits which are used by the control elements in the control path of a digital system. So we can have special sensors for monitoring the quality of water which flows out of the system, and if the quantity of effluence is beyond a certain limit, we can apply the brakes, we can stop the water from flowing out of the system. So the monitoring of the water quality is somewhat analogous to the monitoring of status of data in the digital system. The status of data may be in the form of overflow, or maybe in the form of a divide by zero operation. So depending on the nature and gravity of the exception that has been caused, as indicated by the status bits, appropriate action will be initiated by the control path elements. So the building pipeline analogy, I feel, effectively models the RTL abstraction in terms of the data path and control path. Shift and add serial multiplier can be implemented at the register transfer level of abstraction. So this is a very simple and popular method for multiplying two binary numbers using a digital system. So the first step in implementing the serial multiplier at the RTL abstraction will be to identify the register transfer operations that are going to be involved in the multiplication process. The multiplicand is assumed to be stored in a 5-bit register. A second register called the accumulator is a shift register, which is initially loaded with the multiplier in its least significant bit positions and zeros in the position which will be storing the partial product during the course of the multiplication sequence. the generation of the partial product will depend on the current multiplier bit. At the beginning, we see that the least significant bit is 1. Therefore, the first step is to add the multiplicand to the contents of the partial products register. At the end of the first addition, we shift the partial product by 1 bit position towards the right. Now this serves two different purposes. The first purpose is to shift the partial product, which is part of the multiplication process. The second purpose is to bring the next multiplier bit to the least significant bit position of the accumulator register. The current action that is to be carried out in generating the partial product will be determined by the current multiplier bit. If the multiplier bit is a 1, the multiplicand will be added to the partial product, and if it happens to be a 0, 0 will be added to the partial product. So we see that the second multiplier bit is also 1, which results in the multiplicand getting added to the partial product. Again, after the second addition, the partial product is shifted to the right by 1 bit position. And as a result of the shift, now the current multiplier bit that we are considering is a 0, which indicates that instead of adding the multiplicand, we have to add a 0 to the partial product. And the shifting process again is carried out by 1 bit position. Which brings us to the last multiplier bit, which is 1. This means that again the multiplicand has to be added to the partial product. The sum is shifted for the 4th time, and this completes the multiplication process. So when the number of shifts is equal to the number of bits of the operands, the multiplication process completes. The sequence of register transfer operations identified in the previous slide logically leads us to the development of the Datapath Elements for implementing the multiplier. As already mentioned, we need a register for storing the multiplicand. On the other hand, we need a shift register, which is usually referred to as the accumulator, which holds the current value of the partial product and initially the multiplier. During every shift operation, one of the bits of the multiplier is shifted out. Since the generation of the partial product requires an addition step, obviously we need an adder. And this will be a 5-bit adder since we are dealing with 4-bit operands. The 1 extra bit is required just in case one of the additions generates a carry. One of the operands to the adder is the partial product from the accumulator. The second operand can either be the multiplicand or 0, depending on the current value of the multiplier bit. So this necessitates the use of a multiplexer for routing either 0 or the multiplicand, depending on the least significant bit in the accumulator. The output of the adder, the sum output of the adder, is again routed back to the accumulator, because that forms the partial product which will be used as the operand during the next addition step. We need an add control signal in the accumulator. Now this control signal is required for loading the partial product from the output of the adder at the appropriate time. We need another control signal called the shift signal, which signals a shift, that is a right shift, in the accumulator. Now we can intuitively see that both these signals will be generated by the control path. So this completes the identification of the data path elements for the multiplier. So to sum up, we have an adder, we have a multiplexer for routing either the multiplicand or the 0 depending on the least significant bit in the accumulator, and we have two registers, the multiplicand register and the accumulator register, and the outcome and the output of the adder is routed back into the accumulator. So this finishes the design of the data path. Now once these data path elements have been identified, the rest of the process for implementing these data paths can be carried out using hardware description languages. So we can develop individual behavioral models of the adder, the mux, the register and the accumulator. So the design effort is primarily towards identifying the data path elements and their interconnections. So beyond this level, we need not go down to the gate level as in the traditional design flow. Once we have identified the data path elements and their interconnections, the data path design can be deemed to be complete. The rest of the flow will be in HDLs. The details of the control signals that need to be generated by the control path emerge once the data path elements are in place. This is understandable since the very function of the control path is to regulate the flow and manipulation of data in the data path. Therefore, from the design of the data path, there are two control signals, namely the add and shift signals, which have to be generated by the control path. The function of the add and shift signal will be evident once we analyze the data path. That is, the add signal is required to indicate to the accumulator that the output of the adder is to be updated into the accumulator. And as far as the shift signal is concerned, it indicates that the contents of the accumulator have to be shifted one bit position to the right. In addition to these two control signals, we require an enable signal for triggering the multiplication operation or for setting the multiplication process in motion. So if this multiplier is part of an ALU, for instance, in a processor, this enable signal could be triggered by the loading of a multiplication instruction in the instruction register. So when the enable signal is asserted, the multiplication process is set in motion. The whole operation consists of a sequence of 4 add operations, each add operation being succeeded by a shift operation. Therefore, there are 4 pulses in the add signal, and the shift signal is also pulsed 4 times. In addition to the add and shift, and of course the enable, we need to have a counter to keep track of the number of adds and shifts. This is required for putting an end to the multiplication operation at the appropriate time. Therefore, to sum up, the control elements, the control path elements, need to generate the add and shift signals, and the elements have to wait upon the enable signal. So the whole process is set in motion when the enable signal is asserted. For keeping track of the number of shifts, we need an additional counter. Since the nature of the generation of signals is sequential, we shall require a state machine for generating these signals. Obviously, the state machine will be triggered whenever the enable signal is asserted. The state diagram of the state machine for the control path of the multiplier is shown in this slide. As mentioned previously, the state diagram, the state machine is triggered by the enable input. So whenever the enable input is asserted, the multiplication process is set in motion and the state machine moves from its idle state to the add state. So we have used a Moore state machine representation. Therefore, the add state signifies the assertion of the add control signal. Or in other words, the state machine asserts the add control signal when it goes to the add state. The state machine remains in the add state for 1 clock and it transitions to the shift state if the count happens to be less than 3. And in the shift state, the shift control signal is asserted. So this is in keeping with the sequence that we saw while discussing the timing diagram. That is, the shift signal always succeeds the add signal. Logically, therefore, the shift state in the state machine will follow the add state. Of course, this transition is dependent on the value of the count. Therefore, the state machine has the count value of the counter as one of its inputs. The other input is, of course, the enable signal. When the count is 3, the state machine reverts to the idle state. Rather than moving into the shift state, it reverts to the idle state, and this completes the multiplication operation. The top level RTL of the serial multiplier, which is realized by integrating the data path and control path, is shown in this slide. The next step in the design flow is to model each element in this RTL behaviorally using HDL. Eventually, all these behavioral models are integrated using a structural model, and that will give you a top level design file, which of course will be simulated and its functionality verified, and the top level design file will be eventually synthesized to a target architecture such as an FPGA or an ASIC library. So I think by now it will be evident that the HDL based design flow offers considerable savings in terms of design effort and hence design lead times. The chief effort of the designer lies in identifying the data path and control path elements, and the sequence that we adopted previously for developing the serial multiplier RTL can be followed for identifying the RTL elements of a system. Since by now we have understood what exactly is a data path and what exactly is a control path, it will be appropriate to try to visualize a simple accumulator based processor from the RTL perspective. The accumulator based processor is one of the simplest processor design. Of course, even though it is not current state of the art, I think it will serve the purpose of illustrating how a processor could be represented at the RTL. Those who are familiar with the 8085 processor will identify it as an accumulator based processor. So in an accumulator based processor, all arithmetic operations have the accumulator as one of its operands. The result also is stored in the accumulator. So this considerably simplifies the data path because the ALU needs to be connected only to the accumulator. There needs to be no selection logic for selecting the destination for storing the results of a particular instruction. So in the data path of the accumulator based processor, we have the entire register file including the accumulator being routed through a multiplexer to the ALU as one of the operand inputs. The select line of the multiplexer will be driven by the control path depending on the opcode of the instruction. The opcode, of course, we know that the operand field of the opcode will have an encoding that will indicate the registers to be selected for a particular operation. And this can be used as the select line for the operand selection multiplexer. And as far as the result is concerned, of course, there is no selection. The result is directly wired to the accumulator. Therefore, the only function of the control path in loading the result will be to generate the enable signal for loading the result into the accumulator at the appropriate clock cycle. In the control path of the processor, we have the state machine, which is responsible for generating all the signals in the control bus. Then there is, of course, the instruction register, which holds the current instruction to be executed. Then there is, of course, the program counter, which keeps track of the address of the instructions, and the instruction decoder, which segregates the various fields of the instruction that is loaded to the instruction register. In the light of the understanding of the RTL concepts that has been provided in this lecture till now, we shall look at digital design from a higher level of abstraction, that is the algorithmic level. Over the last couple of decades, there has been an increasing requirement for automating the RTL design process. With increase in complexity, the generation of RTL itself has become complex, and hence, in order to reduce design lead times, there has been a pressing need for developing techniques to automate the generation of register transfer level designs from algorithmic specifications. The technique of high level synthesis, or HLS, basically addresses this problem. So high level synthesis is defined as the process of translating an algorithmic description into an equivalent RTL. So in this lecture, we will provide a brief glimpse into high level synthesis. We will be taking up high level synthesis in detail during the later part of this course. But since we have introduced RTL at this point of time, I thought it will be better if we provide a brief glimpse into what exactly is high level synthesis. So I have taken up a very simple, trivial example of a DSP filter. So we all know that filters are represented by difference equations, which can take the form the simple form that is shown here. So this is an algorithmic description that may be provided in C or using a MATLAB code. Now in a high-level synthesis, in a typical high-level synthesis flow, the high-level synthesizer will parse this algorithmic description and it will translate it into an intermediate stage called a data flow graph. So the data flow graph will be a graph that will have nodes corresponding to each operation that is depicted by the equation. So in the data flow graph corresponding to this DSP example, you can see that there are two multiplication operations and one addition. Now if you try synthesizing this particular data flow graph, in a naive implementation, you can have two multipliers and one adder. That is, if you directly map this data flow graph into the equivalent hardware, you will end up with a resource allocation of two multipliers and one adder. But typically most of these design flows are constrained by the number of resources available. So in this case, there may be a constraint that you can use only one multipliers, because we all know that multipliers generally take up a lot of area, especially the parallel multipliers. Therefore, if we are constrained at using just a single multiplier and a single adder, then we need to redefine this data flow graph in such a way that only a single multiplier is used. So we resort to a process of rescheduling the operations and generate a rescheduled DFG, which is shown on your right. So in this data flow graph, you can see that in the first cycle, the first multiplication is executed, and in the second cycle, the same multiplier is used to complete the second multiplier operation, and finally the addition happens in the third cycle. So in order to store the outputs of the multiplication operations, obviously we require registers. So intuitively, just by looking at this DFG, we can say that the data path of this particular system will consist of a single adder, a multiplier, and registers. But there is some more to it, because the DFG does not reveal the requirement of steering logic that is required for routing the operands to the multiplier. So this will become evident when we develop the data path in the next slide. The DSP filter, the sharing of the multiplier necessitates the use of a pair of muxes for routing the appropriate operands to the multiplier. So this is controlled by the cell line, which is generated from the control path. Therefore, when the value of the cell is 0, the operands for the first multiplication, namely k1 and xn, are seen by the multiplier. In the second cycle, when cell is 1, the operands for the second multiplication are seen by the multiplier. So this scheduling is carried out by the control path. At the output of the multiplier, you can see a pair of registers. These registers are required because the outcome of the multiplication process in the first and second cycle, they are used up. They are used by the adder only in the third cycle. So there has to be some storage for the results of the multiplication so that they can be read by the adder during the third cycle. And for loading these registers at the right clock edges, there are two enable signals that are provided, which are also under the control of the control path. So just as in the case of the serial multiplier, the moment the data path elements are in place, we get a fairly complete picture regarding the signals that need to be generated from the control path. In this instance, the select signal cell and the two enable signals EN1 and EN2 have to be generated from the control path. And if we list out the conditions of these signals, the logic levels of these signals at each cycle, we will start with the cell becoming 0 because the operands for the first multiplication have to be routed to the multiplier. And the enable for the register R1 has to be asserted because at the end of the cycle, the result of the first multiplication has to be loaded into R1. And of course, the enable 2 is deasserted. In the next cycle, the select line becomes 1 because the second multiplication has to be performed. The enable for the first register is deasserted because we have to retain the result of the first multiplication, which is now stored in the register. And the enable for the second register is now asserted because at the end of this cycle, we need to load this register R2 with the result of the second multiplication. Finally, in the third cycle, we deassert both the enables because we want the registers to hold their data. And of course, the cell is a don't care, so we can either add a 0 or a 1 to the cell line in this cycle. So the control action basically is very simple in this case. That is, the control path is required to generate a sequence of 3 numbers 0, 1, 0, 1, 0, 1 and say 0, 0, 0. So every 3 cycles the sequence gets repeated. From this sequence it follows that the implementation of the control path will be extremely simple. It will just consist of a sequence generator which can be very easily modeled in an HDL file. Therefore, the sequence generator will continuously generate a sequence 0, 1, 0, 1, 0, 1 and 0, 0, 0, which is repeated as long as the hardware is functioning. So such a design where the control actions are relatively simple and most of the functionality is taken up by the data path is called a Datapath Intensive design. The control sequencer for the DSP filter, as mentioned in the previous slide, will continuously generate the sequence 0, 1, 0, 1, 0, 1 and 0, 0, 0. Of course, it is assumed that every 3 cycles you will have a fresh set of inputs at the input buses of the filter. Since this is a data path intensive design, the control implementation is quite simple and straightforward. On the other hand, if you have a control intensive design where there are a lot of control actions to be performed, the control path will consist of a more complex state machine with associated registers and counters and other sequential elements. Digital systems can be classified into data path intensive and control intensive based on the nature of their RTL models. In Datapath Intensive designs, most of the hardware will be dominated by Datapath Elements such as arithmetic circuits and registers and associated steering logic like muxes and decoders and demultiplexers. As far as the nature of the data that flows through these systems is concerned, mainly these are continuous streams of data which have high degree of spatial and temporal locality. This is a trait that we usually observe in applications such as DSP, image and video processing. So you have a continuous stream of data that is coming into the system, and this flows through the system, and it is subjected to a lot of manipulations in the form of filtering and other operations. And finally you have an output stream flowing out of the system. So basically most of the operations are carried out on the data. And another important point to be noted here is that in these systems, the nature of the output is not monitored by the hardware. That is, at the end of a filtering operation, the type of data that is generated as part of the filtering is not monitored by a status or flag bit. So it is just a continuous stream of data coming in and a continuous stream of data going out. And as far as the control path is concerned, as we saw, primarily the control action will be implemented by a set of simple sequences. In control intensive designs, there is minimal of data processing. On the other hand, the nature of the data is critical, because there may be control actions which need to be taken based on the value of a data or based on whether a data is exceeding a particular threshold and so forth. For instance, in a plant controller system, suppose we have a digital input coming from a sensor. Now if this input exceeds a threshold, there needs to be some control action that has to be initiated. So in such control intensive applications, the nature of the data is critical. As a result, all these systems have plenty of registers which store status and control information. And since the functioning of the system depends on the monitoring of the nature of data and initiating control actions based on the status of the data, the control path also is correspondingly complex. Therefore, as mentioned earlier, we require complex state machines, and sometimes the control action might require a dedicated processor with its own set of firmware, or in some cases the control path is implemented by programmable logic controllers. To sum up, the register transfer level, or RTL, is the ideal level of abstraction for modeling a system using hardware description languages. It provides a level of abstraction where the behavior of the system is adequately captured, just as in the case of an algorithmic description. At the same time, it is of a sufficiently lower level so that the cycle accurate description of a system can be extracted from the RTL model, which is something that is not possible using an algorithmic description. So, to put it in a different fashion, the RTL abstraction is an intermediate level of abstraction between the algorithmic level and the gate level. An RTL model identifies the data path and control elements in a design. The data path elements are primarily involved in the flow and manipulation of data, and they comprise components such as registers, ALUs, buses, and steering logics such as multiplexers and demultiplexers. On the other hand, the control path basically control the flow of data through the data path. So as we saw earlier, if we look at this from the analogy of a building pipeline, the data corresponds to the flow of water. The registers are analogous to the storage of water in storage tanks, and the control path is provided by the use of taps and valves for controlling the flow of water. So basically the control path elements control the flow and manipulation of data in the data path. So from the characteristics of an RTL model, we can determine whether a design is datapath intensive or control intensive. In datapath intensive designs, most of the design is comprised of datapath elements such as arithmetic circuits, registers, and steering logic. And control is implemented using very simple circuits such as sequences. Datapath intensive designs are usually found in applications such as digital signal processing, image processing, and video processing. On the other hand, in control intensive designs, the control path is very complex, which is implemented using complex state machines or even programmable processors with their own firmware. Control intensive designs find application in domains such as networking and process control. Finally, we have the high-level synthesis flow, where an algorithmic description is automatically translated into an RTL model. Now, high-level synthesis has become very popular in the past couple of decades, primarily driven by the need to handle very complex system descriptions that can be easily translated into an RTL so as to reduce the design lead times.